So let's go ahead and talk about what I think are the other two tests or the other tests we're going to. So far we have the following, just to kind of sum up the tests that we have so far. We have the nth term test, also known as the test for divergence. And again, that just says that if the limit as n goes to infinity of a sub n is not 0, then the series for that sequence must diverge. And then we also have the test that says, essentially, I would call it the geometric series test, I suppose. Basically, if you have a series that is typically written as sum a times r to the kth power, which is, a times r plus a times r squared plus a times r cubed plus so on and so on and so on forever and ever and ever. Essentially, each subsequent term multiplying by the same ratio to get to the next term. If that's your series, then this series converges if the absolute value of r is less than 1, it diverges if the absolute value of r is greater than or equal to 1. By the way, just to be kind of super clear about this, people sometimes write this instead as r being between -1 and 1. People write this sometimes instead as r bigger than or equal to 1 or r less than or equal to -1. Same thing. And then we also recently just talked about the p series. So the p series test just says that if you have the sum from k equals 1 to infinity of 1 over, let me get this right this time, k to the pth power, that's going to converge if p is greater than 1, diverge if p is less than or equal to 1. In fact, there was something I know. I want to do a couple examples, and then we'll talk about the ratio test. Yeah. So I should say the reason the p series works, it actually comes from another test, which is called the integral test. But we're not going to learn that in this class. At least it's not on the syllabus, so I wasn't planning on talking about it. But I might just, I kind of feel like it's worth mentioning here, though. I'm gonna hit you with some pictures here. But actually, yeah, let's look at. No, we don't need to get that complicated. I don't know. I feel like it might be worth kind of seeing like why that actually works. So let me just show you. Yeah, because we've talked, let me ask you, Caroline. We've talked about improper integrals, right? Like integrals to infinity. That was last quarter, I think. I know it's been a while. Yeah, okay. All right, that's what I thought. So let me just show you two examples of why the p series stuff kind of works. And again, they're going to be kind of the classic examples. So let's say we wanted to look at the sum from k equals 1 to infinity of 1 over k squared, which is 1 plus 1/4 plus 1/9 plus 1/16, and so on and so on and so on. And I think he said in class that this adds up to something, I think it adds up to pi squared over 6. You don't need to know that, but like it does converge, and it converges to pi squared over 6. But the point is, I would like to talk about how we can see it actually converges other than, right? We know because it's a p series with p greater than 1, it converges, but let's actually see why. And I will point out just, it's always a good thing to think about. Does the nth term test work here? I'm always thinking in the back of my mind, does the nth term test work? And it doesn't, because the limit as n goes to infinity of my a sub n, which is the limit as n goes to infinity of 1 over n squared, I used n instead of k, is equal to 0, which means we know nothing. I feel like we could start calling the nth term test the Jon Snow test, right? If you watch Game of Thrones, you know nothing, Jon Snow. I feel like that works. Some pop culture there, some old pop culture, right? But okay, whatever. So let's say we wanted to estimate the 100th partial sum. So S100, which is the sum from k equals 1 to 100 of 1 over k squared, which is 1 plus 1/4 plus 1/9 plus all the way to 1 over 99 squared plus 1 over 100 squared. So we're going to draw some stuff here. So first we're going to draw the function 1 over x squared. So here I've got y equal to 1 over x squared. Now check this out. What I'm going to do is I'm going to draw some rectangles that have the same areas. So if I start at 1 here, well then this rectangle from 1 to 2 with a height here, that rectangle has an area of, well, the base is 1 and the height is also 1 because of it. And I know it doesn't look like the scale, but if I plug in 1 here, 1 over 1 squared is 1. So this first rectangle has an area which is our first term, 1. And this next rectangle I'm going to draw has an area that's equal to the second term of our sequence, which is 1/4. And you can kind of see that this is going to go on and on and on and on. So if I go way, way, way out here to some nth term, right? If I plug in n here, and this is n plus 1, this rectangle here has an area of a sub n. So here's what I'm going to say right now. If I add up all those rectangles, then I can say that, well, a sub 1 plus a sub 2 plus a sub 3 plus all the way to a sub n is certainly the area of those rectangles is bigger than the area under the curve. So look at the area under the curve, I'm going to shade in here, right? You can see that the area of the rectangles is more area. So these rectangle areas all added up together are going to be bigger than or equal to the integral from 1 to n plus 1 of my function 1 over x squared dx. And I'm going to draw another picture as well. So same picture, kind of. Same function. Kind of, right? I mean, same function. But now I'm going to draw the rectangles that are underneath. So from 1 to 2, I'm going to draw the rectangle that has a height when I plug in 2. So plugging in 2, I'm going to get a height of 1/4. So this rectangle has an area that's a sub 2, which is 1/4. And the next rectangle is going to have an area of a sub 3, which is 1/9. And if I go all the way out to, let's see, let me show you this right. So I'm going to go all the way to n minus 1 and then n, and I'm going to use the lower value here. Right, this last rectangle has an area of a sub n. And these rectangles add up to an area that is less than if I do the integral from 1, well, not quite, so I have to add on one thing. So right, all this area here in blue, this blue area is more than the rectangle area. So the rectangles, A1, sorry, oh, I'm missing the term A1 though, right? So what I have to do is I have to say, well, I'm going to say that's less than or equal to if I add on A1, right? Because I have A2, A3 all the way to AN. So if I add on A1, then this area in blue is certainly bigger than the area in red. So right, so just to kind of clarify, what I'm really saying here is, right? Yeah, A2 plus A3 plus, oops, sorry, you can't see it. A2 plus A3 plus all the way to AN is less than or equal to the area. And then I'm adding A1 to both sides. So again, what I'm saying here is that this sum is bigger than this blue area here. And this sum is less than this blue area here, but I have to add on A1. Okay. Any questions? Cool, we don't have questions. Okay, cool. So then the whole reason I'm talking about this, and again, this is super this is a little extra, but I really just want you to see why we believe the PE test actually works. Because now what I'm gonna do is I'm gonna say, well, I can see that if specifically I want to do S100, well, I can say if I let n equal 100, then the integral from 1 to 101 of 1 over x squared, well, the integral of 1 over x squared is negative 1 over x from 1 to 101. That's going to be negative 1 over 101 minus negative 1. That's going to be, oops, 101, sorry. So that's going to be 101 over 101 minus 1 over 101, which is going to be 100 over 101. And then this integral over here, well, that's going to equal, so my a sub 1 is 1. So 1 plus the integral from 1 to 100 of 1 over x squared is going to be, so again, same integral. The integral of 1 over x squared is negative 1 over x, but now I'm going from 1 to 100. So I'm going to get, I feel like I made a small mistake here. No, that should be right. Okay, yeah. Interesting. So I'm going to get, let's see, that's going to be equal to 1 plus, let's see, so if I plug in 100, I get negative 1 over 100. If I plug in 1, I get negative 1. So here I've got 1 plus 99 over 100. So what I can say is that this S100 is between 100 over 101, which is just a little bit less than 1, and 1 plus 99 over 100, which is just a little bit less than 2. The point, though, is that essentially we can take the limit of both of these and say that if you just keep adding on terms, you can just let the integral go further and further and further out. So here's the idea. Sorry, there's no one here to tell me I'm off screen. So if I'm off screen, let me know. So the idea basically is we're going to take this inequality and take the limit of everything. So the limit as n goes to infinity of the integral from 1 to n plus 1 of 1 over x squared dx is equal to the limit as n goes to infinity of negative 1 over x from 1 to n plus 1, which is going to be the limit as n goes to infinity of negative 1 over n plus 1 minus negative 1 over 1. That's going to go to 0. So we end up with positive 1. And the limit as n goes to infinity of the other thing, which is this part here, the a sub 1 plus the integral from 1 to n, it's going to be 1 plus the integral from 1 to n of 1 over x squared dx, which is going to be the limit as n goes to infinity of the, oh, sorry, I forgot the 1 here, of 1 plus the integral of negative of 1 over x squared is again negative 1 over x from 1 to n. So we get the limit as n goes to infinity of 1 plus negative 1 over n minus negative 1. This part again goes to 0. So I get 1 plus 1, which is 2. And then what we're going to say is, well, our series, our infinite series has to be between that. So the limit as n goes to infinity of the sum from k equals 1 to n of 1 over k squared, which is just the sum from k equals 1 to infinity of 1 over k squared, must be between those two numbers, which tells us it converges. So that's kind of the whole idea, that we can say that since this partial sum is trapped between these two integrals, and each of these integrals converge, then the partial sum also has to converge to a finite sum. That's kind of the whole idea. So this shows that since, I'm gonna write it this way, the partial sum from k equals 1 to n of 1 over k squared is trapped between these two integrals, a sub 1 plus the limit, or plus, oops, the integral, variable, sorry, from 1 to n of 1 over x squared dx, and it's bigger than the integral from 1 to n plus 1 of 1 over x squared dx. Since this inequality is true and the limit as n goes to infinity of both this and this exist, sorry, you can't really see that. Then the middle thing has to exist. Converges. So since these two limits converge, this series also converges because it's between two. Now I will point out, this doesn't actually say what the series adds up to, right? We're just saying we know it's between 1 and 2. We don't actually, well, we do actually know what it is because someone else found it using some other method, pi squared over 6, or I think, which is certainly between 1 and 2, but we don't actually know the value. So long story short, the P series works. You could also show a similar kind of thing for 1 over n. If you wanted to show that 1 over n diverged, you could show that both the intervals it would be between would also diverge, which shows divergence. But I don't think we need to do that unless you really want to. So that's kind of the deal. That's why the P series really works, is because you're stuck between two intervals that converge, or stuck between two intervals that diverge, depending on what you've got. So I think there was something else I wanted to say there. Oh, I know. It's okay. Okay, you can totally leave early. I can talk to Noah. Let me just say one more thing real quick. Is that it's kind of like the squeeze theorem, where you had a function between two other functions and you found the limit of both of them and they both equal the same thing. So the limit of the middle thing equals the same thing. This is not quite the same. We're showing that both of these limits are finite. And so the thing in the middle has to also be finite. So that's kind of the deal. But yeah, you're welcome to go if you need to go, or whenever you need to go. I will talk to the room about a couple of examples. You're welcome. So let's see here. Oh yeah, I know what I was gonna do. Let's do, so now that no one's here, I can go wow. All right, so let's talk about a couple examples of doing some P series problems and some oh yeah, P series is interesting. And some what was the example I was gonna do? Oh, some geometric series. So geometric series can be a little bit challenging. I have a couple of examples here. Let me grab them real quick. Yeah. So let's look at something like the sum from, I'll use k equals 1 to infinity of, let's try this. Let's say we had 6 times 3/4 to the nth power. Well, that's pretty straightforward. That's going to converge. This definitely converges because our r, which is 3/4, is between 1 and -1. Or in other words, I would just write really because r equals 3/4. But then you can write and the absolute value of 3/4 is less than 1, if you really need to say that. And then if it's geometric, we usually are also asked what it converges to. So this converges to, again, I'm always just going to write first term over 1 minus the ratio. So we have the sum from k equals 1 to infinity of 6 times 3/4 to the nth power. It's going to converge to, or it's going to equal the first term. So 6 times 3/4 to the first divided by 1 minus the ratio, which is 3/4. Simplifying this. So I wouldn't actually simplify this fraction here. What I would say is I have 6 times 3/4 divided by 1 minus 3/4, which is 1/4, which is going to be 6 times 3/4. I feel like I did this example last time. Maybe I just make up the same examples all the time. Times 4 over 1. The 4's cancel and you get 6 times 3, which is 18. I feel like we had one last time, it was 18. Oh well. Let's look at another example. Let's say I wanted to find the sum, or so again, when I'm writing these, the question I'm asking is, does this converge or diverge? And if it converges and it's geometric, if it converges, what does it converge to? Okay, so I should try and stay out. There's no one to check me here, so I better really make sure I stay in frame here. Yeah. Also, there's something weird over here. Let me just check one thing here. There we go. That's That's better. Okay, cool. So, let's look at another example. Let's say we have the sum from k equals, I'm gonna start at k equals 2, just to change it up a little bit, to infinity of, I'm gonna write this a little bit different. Let's say I had 5 times negative 3 to the n over 2 to the 2n plus 1. That's not, it's kind of lame because I kind of make the same ratio. Oh, that's fine. So when you have something like this, where you've got things raised to the nth power, it can be kind of unclear what your ratio might be. One way to attack this is to start writing out terms. So we start with k equals 2. My first term is going to be, let's see, 5 times negative 3 squared over 2 to the 4 plus 1 is 5. And then my next term is going to be, if I plug in 3, 5 times negative 3 to the 3rd over 2 to the 7th. My next term is going to be 5 times negative 3 to the 4th over 2 to the 9th. And it goes on and on and on. You could use this to identify your ratio, because I can see that to get from this term to this term, I multiply by, let's see, a negative 3 on top and a 2 to the 2nd on the bottom. And the same thing is true here. If I multiplied, what I multiplied by this term to get this term, or essentially this term divided by that, if you want to do it that way, is again a negative 3 on top and a 2 squared on the bottom. So it looks like here my ratio is negative 3/4. And again, we're going to get convergence because we can see that our ratio in absolute value is less than 1. Another way to see what the ratio is without having to write out terms, because the terms can get messy. I do recommend, though, if you're thinking about trying to see if what the ratio is this way, don't simplify the terms, right? Writing it like this, where I just write powers like this and this, it's really easy for me to see that, oh, from here to here, I had to multiply by a negative 3 to get from negative 3 squared to negative 3 cubed. And from here to here, I had to multiply by a 2 squared on the bottom to get from 2 to the 5th to 2 to the 7th. But if you don't like that, another way to do this is to kind of rewrite your expression. So I'm going to rewrite my expression, simplifying a little bit. So I've got 5 times, I've got a negative 3 to the n on top, and then on the bottom, I'm going to break apart the 2 to the 2n plus 1 as 2 to the 2, or let's say 2 to the 1 times 2 to the 2n. I'm going to think of this as 5 over 1 just to make life a little easier. And then I'm going to rewrite the summation as the sum from k equals 2 to infinity. I'm going to bring the 2 to the 1 over there because it's not really changing. So I'm going to have a 5 halves. And then I have negative 3 to the n, and 2 to the 2n is really 2 squared to the n. Or if you prefer, and I do prefer, the sum from k equals 2 to infinity of 5 over 2 times negative 3 to the n over 2 squared is 4 to the n. And then finally, if you have something to the n over something else to the n, you can combine that as one fraction to the n. So I can rewrite this as the sum from k equals 2 to infinity of 5 halves times negative 3/4 to the n. And then once you have kind of something raised to the n power and you don't have any n powers anywhere else, like over here, I couldn't have said my ratio was negative 3 because I didn't have all the other to the n's dealt with. But now that I've got everything to the n and then some constant over here, I can say, oh, that has to be my ratio. And then we get convergence for the same reason. Our ratio is negative 3/4, and the absolute value of negative 3/4 is less than 1. So then we can also see what this converges to by, again, doing first term over 1 minus your ratio. So my first term, if I plug in, I could either plug in here or go back over here. So I probably do it here. So my first term is going to be, if I plug in k equals 2, 5 halves times negative 3/4 squared over, if I plug 1 minus my ratio of negative 3/4. So now I'm going to have, let's see, I'm going to simplify this. I'm going to have 5 halves times 9/16 over 1 plus 3/4 is 7/4. So I would simplify this. I've got 5 times 9 is 45. So 45 over 2 times 16 is 32. Multiplied by the reciprocal 7/4 is 4/7. So then I cancel a 4 here and a 4 here and end up with 45 over 56. So that's a pretty common thing to see is people trying to write things in a little more of a confusing way, not to be confusing on purpose, just to make it a little more challenging. Let's try a couple more. Let's say I wanted to find the sum from k equals, sure, k equals 10 to infinity of, or I should say, we're going to test for convergence, divergence, sum from k equals 10 to infinity of, let me think for a second here. Sure, I kind of like this. Let's say we had, yeah, 5 to the 2n minus 3 over 4 to the n plus 1. Yeah, that works. So again, just like the last problem, I really want to re-express this as just something raised to the nth power and then multiplied by whatever constants left over. So I'm always going to pull off the kind of minus or plus parts of the powers. So I'm going to rewrite this as the sum from k equals 10 to infinity of 5 to the negative third times 5 to the 2n. And I would probably just break out the pieces that didn't have n's. So over here, I'm going to have a 4 to the 1 and then a 4 to the n. And then I'm going to rewrite this as the sum from k equals 10 to infinity. You might consider simplifying this. It's not super necessary. The one thing I might do for sure, though, would be write it as 1 over 4 times 5 cubed. Just I like positive powers if I can help it. And then over here, I'm going to have a 25 to the n, right? Because 5 to the 2n is 5. 5 to the 2n is 5 squared to the n, which ends up being 25 to the n over 4 to the n. I was trying to make this challenging too, but it's really not. Like you can kind of see, I kind of made this a 3. Oh well, such is fine. So then we can see that this is the sum from k equals 10 to infinity. If you wanted to simplify this, you could. 5 cubed is 125, and 125 times 4 is 152, which is 250 times 500. So you can write this as 1 over 500 times. You don't really need to do that though, because you've got 25 fourths to the n, and we can see that this is going to diverge because our ratio, which is 25 fourths, is bigger than 1 in absolute value. Diverges. We could have approached this the other way if you wanted to, right? You could have started writing out a couple terms. Again, if you see basically all things raised to like nth powers or 2n powers or 3n powers, then you can start by saying, oh, I'm just going to write some terms. My first term is kind of weird though. It's 5 to the 2 times 10 is 20 minus 3 is 17 over 4 to the 10 plus 1 is 11. And then my next term would be, so then I'm plugging in 11, I'm getting 22 minus 3, which is 19 over 4 to the 12. And then my next term is 5 to the 21 over 4 to the 13th. And then you can see, oh, every time I'm multiplying by 5 squared over 4. Multiplying by 5 squared over 4. So my ratio is definitely bigger than 1. Let's look at one more example like this, and then we will talk briefly about the ratio test. So, I guess P-series, we can talk about the P-series. It's just kind of boring, right? There's not a lot of examples other than it's like if you have 1 over n to the P. There's a couple of things we can say about it though. But let's go ahead and talk about this next example. Let's see with the sum from k equals 4 to infinity. Let's make up something kind of fun. Really, these get to be kind of not super exciting. Let's say we had 2 to the 3n plus 5 over 3 to the 2n minus 1. So when I look at this, I'm really kind of thinking about what's raised to the nth power. So I have 2 to the 3n, I'm ignoring the 5. I really have 8 to the n, right? Because 2 to the third is 8. And over here, 3 to the 2n is really 3 squared to the n, which is 9 to the n. So what I'm going to end up getting is something like 8 to the n over 9 to the n. I'm going to have a ratio of 8 ninths. Well, I'm still going to write it out, but it's good to think about what's going to happen before we actually do it. So I'm pretty sure I'm looking for convergence here, or that I'm going to get convergence. Let's find out. So if I write this, I can write this as, again, 2 to the 5th over 3 to the negative 1, breaking off the not n part. And then my 2 to the 3n is going to be 2 to the 3 to the n. And my 3 to the 2n is going to be 3 to the 2 to the n. So I could rewrite this as the sum from k equals 4 to infinity, I would totally rewrite this as 3 times 2 to the 5th times, that's 8 to the n over 9 to the n, which is 8/9 to the nth power. And then this definitely converges, and I would say it converges to, well, I'm going to get, let's see, my first term over 1 minus ratio. So my first time I'm plugging 4, so I'm going to get 3 times 2 to the 5th times 8/9 to the 4th over 1 minus 8/9. And I probably wouldn't do much simplifying here unless I was really asked to. We could simplify this a tiny bit. I'm going to get 3 times 2 to the 5th is 32. And then you're going to have an 8 to the 4th over 9 to the 4th. And dividing by 1/9 is the same as multiplying by 9 over 1. So then you can cancel one of these 9s and say it's still pretty gross though, right? I have 3 times 32 times 8 to the 4th divided by 9 cubed. The last thing you could do is cancel, right? 9 cubed is 9 times 9 times 9. You can cancel a 3 with one of those 9s. So you're left with 32 times 8 to the 4th is 2 to the 3rd to the 4th, which is 2 to the 12th. And then the 3 and the 9 cubed, I'm going to get a 9 times the 9 times a 3. Again, none of this is really important. I should probably just stop, but I'm done. I can't now. So I would finally simplify this as 32 is 2 to the 5th times 2 to the 12th, and 9 times 9 is really 3 squared times 3 squared times 3. Just to write this all as just powers of one thing. So I really have 2 to the 17th over 3 to the 5th. Which I know is a dumb answer, but oh well, it is what it is. You could get a terrible fraction, some power of 2 over 243, but whatever. But really on like an exam or even on a homework problem, I would probably stop like here. Just be like, or maybe this next step. Like I feel like this is a reasonable stopping place, but we shouldn't do all the rest of this. It was kind of silly. All right, let's talk about some P-series examples just for a minute. So for example, I could say, so these are just going to be converge or diverge questions though. Because for P-series, we are not expected to know what they converge to. And some of them literally can't be found. For example, what about the sum from n equals 1 to infinity of 1 over n cubed times the square root of n? Well, I'm going to rewrite that as the sum from n equals 1 to infinity of 1 over n cubed times n to the 1/2, which is really the sum from n equals 1 to infinity of 1 over 3 plus a half is 3.5, or if you prefer fractions, I think a decimal might be better here actually. To me, it's easier to see that 3.5 is bigger than 1 rather than 7/2. So I would say, oh, this converges because our power P is 3.5 and that's bigger than 1. Technically, to be a P-series, we have to start at 1 and go to infinity of 1 over that. But really, we can be a little bit more general. Really, you could say, well, for example, what if I have the sum from n equals 5 to infinity of 1 over, what have I got here? Sure. Oh, that's a good question. N to the 4th. Well, technically, this isn't a P-series because I'm starting at the wrong place. But I can say this definitely converges because this series from n equals 1 of 1 over n to the 4th converges. P is equal to 4, greater than 1. And then, right, if this converges, this thing that has less terms in it also must converge, right? This here is 1 plus 1 over 2 to the 4th, plus 1 over 3 to the 4th, plus 1 over 4 to the 4th, plus 1 over 5 to the 4th, plus 1 over 6 to the 4th, forever and ever and ever. And what we're saying is that converges or adds up to some finite number. And all we're saying over here is, well, I've just got less terms. Here I'm just starting off with 1 over 5 to the 4th, plus 1 over 6 to the 4th, plus 1 over 7 to the 4th. But if all of this converges, then certainly this part here converges too, which is just this part over here. So basically, you can really start wherever you want. if some series converges, some series that has less terms will also converge. Similarly, that's also true for divergence. If I do like the sum from n equals 4 to infinity of 1 over the square root of n, well, that's going to diverge because this other series that starts at 1 of what from n equals 1 to infinity of 1 over the square root of n also diverges as a p series with p equal to 1/2. Right, the power is 1/2, which is certainly less than or equal to 1. So right, this diverges, right? Here your terms are looking like, let me write them in red here. 1 over 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus 1 over the square root of 5, so on, so on, so on. And what we're saying is this diverges to infinity. The to infinity part is not necessary, but I just thought I should say, oh darn, I didn't check in on myself. Hopefully you guys have been able to see all the things. This diverges to infinity, and now we're saying, okay, great, subtract off these first 3 terms. So if all this forever and ever and ever adds up to infinity, then I'm pretty sure that this also diverges to infinity because, right, infinity minus 1 plus 1 over 2 plus 1 over 3, that's still infinitely large. So we can definitely say, oh yeah, this thing here, which is just 1 over the square root of 4 plus 1 over the square root of 5 plus 1 over the square root of 6, so on and so on and so on. This must diverge as well. So basically, convergence or divergence isn't affected by how far into the series you start. You can start at 1, but you can start at 5, you can start at 10, you start at 1,000,000. It's not going to change whether or not something diverges because you're just adding on or subtracting off a finite number of terms. And a finite number of terms can't affect the overall finite or infiniteness of your summation. Also, just to kind of piggyback on that, you can multiply by constants that won't affect anything as well. So in a similar way, we can totally say that the sum from k equals 1 to infinity of, I don't know, say like 5 over n to the 6th, this, well, in fact, we can even just factor out the 5. We can say that's equal to 5 times the sum from k equals 1 to infinity of 1 over n to the 6th. And then since this is convergent as a p series, right, this is a convergent p series with p equal to 6, which is certainly, I did the thing where I wrote n's instead of k's. Terrible, sorry. There should be a k there. It's not too terrible, but it's just I'm so used to using n, I'm sorry. So this is a convergent p series with p equal to 6, which is certainly bigger than 1. So that's why it converges. So since this converges, certainly 5 times it is also a finite thing that converges. So this is convergent. So constant multiples don't affect convergence or divergence either. One way to think about this, if you like, is this sum here really is just, right, it's 5 over 1 to the 6th, plus 5 over 2 to the 6th, plus 5 over 3 to the 6th, plus 5 over 4 to the 6th, and so on and so on and so on. And if you factor out the 5s, that's just 5 times 1 over 1 to the 6th, plus 1 over 2 to the 6th, plus 1 over 3 to the 6th, plus 1 over 4 to the 6th, which literally is just 5 times the sum from k equals 1 to infinity of 1 over k to the 6th. One of these days. And again, converges. Again, we don't know what it converges to, but we do know that it converges. Let's look at one more example. It's a little trickier. Sum from k equals 1 to infinity of, what do we got here? Where'd you go? Yeah, let's write this as 1. Sure, let's say it's 5. Yeah, 5, sure. 5 plus n over n squared. So this one's not super clear. I would break it up as the sum from k equals 1 to infinity of 5 over n plus n, 5 over n squared plus n over n squared, which is going to equal the sum from k equals 1 to infinity of 5 over n squared plus the sum from k equals 1 to infinity of 1 over n, or n over n squared, but that uses 1 over n. And then I could even bring out the 5 and say that's going to equal 5 times the sum from k equals 1 to infinity of 1 over n squared plus the sum from k equals 1 to infinity of 1 over n. This first portion of it converges, right? It's a p series. P is equal to, darn, I did the n thing again. Just terrible, 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 terrible. I can't help it. It's ingrained in my brain. Sorry. K. So incredibly terrible. K. Okay. Sorry about that. Okay. So this converges as a p series with p equal to 2, which is bigger than 1. And this one diverges as a p series with p equal to 1, which is less than or equal to 1. And if you have something that converges, means adds up to a finite thing, plus something that diverges means adds up to an infinite thing, or maybe does some bouncing around back and forth, never gets close to a number. The whole thing is going to diverge. So when you have two things together, if one piece diverges, the whole thing diverges. So this is divergent. How exciting. So next time, I think I'm gonna end up canceling class on Friday because I have things to do on Friday. And I promised my wife that if I taught classes this quarter, I would potentially cancel a class and go do a thing during the day. So we're gonna do a thing during the day. But maybe on Monday we'll talk about the ratio test. So the ratio test very, very simply says basically that if you have some series, the sum from k equals 1 to infinity of a sub k, if we look at the limit as k goes to infinity of a sub k plus 1 over a sub k in absolute value, and if that limit exists, well, one of three things can happen. If the limit is less than 1, then the series converges. The idea being essentially what we're taking the limit of the ratio here is that basically the next term of the previous term. So we're saying the next term is some fraction of the previous term that's small. Oh, I got signed out. That's weird. I don't want to be signed out. Hopefully I'm still recording. We will see. Okay. Anyway, I can say this again later. And then if your limit is larger than 1, then the series diverges because the terms are kind of getting bigger. And sadly, if the limit is equal to 1, then the test is inconclusive. And all that means, it's kind of like the nth term test when you get 0. We have to do more work, do more other work. The reason this really works is because, well, let me actually, I got time. Let's see here real quickly. Yeah. Where'd you go, ratio test? Yeah, so let's actually, so I'm just going to walk through this example real quick, and then we can talk about it again another day. So here's kind of the idea with the ratio test. Oh, hopefully you all can see this pretty well. So geometric series, one more time. Here's a geometric series. Our ratio is 1/2. Every time we're multiplying by 1/2 to get to the next term. Cool. So to find the ratio R for any geometric series, we can just divide any term by the previous term, like I've been talking about, right? If you do 12 divided by 24, you get 1/2. 6 divided by 12, you get 1/2. I usually phrase it as what do you multiply by this term to get to the next term, but that's the same question as what do you, this divided by this equals what? So this divided by that's 1/2, that divided by that's 1/2, so on and so forth. So basically, we're looking at the ratio being the next term divided by the previous term, an plus 1 over an, which definitely comes back to this thing right here. The idea of our next test is that some series, while they aren't actually geometric, they start to behave like a geometric series as we go on and on and on. For example, the series of n squared over 2 to the n. We get 1/2 plus 4 over 4 plus 9 over 8 plus, if we go way out, 100 squared over 2 to the 100, 101 squared over 2 to the 100 plus way out here. So the idea being like we've got something that's kind of behaving in a geometric sort of way, right? If you go from this term to the next term, you're essentially multiplying by 1/2. I mean, yeah, the top is getting slightly bigger, but really not a lot. If you look at this here, if you look at the 101st term over the 100th term, you're getting 101 squared over 2 to the 101 over 100 squared over 2 to the 100, which simplifies as 101 squared over 2 to the 101 times 2 to the 100 over 100 squared, and 2 to the 100 over 2 to the 101, right? This part over this part is just 1/2. And 101 squared over 100 squared is just 101 over 100 squared, which is 1.01 squared, which is 1.0201, which is very close to 1. So we're getting 1 there. So this, when you go way out here, the numbers get really close to 1/2 times 1. This looks funky. Oh, that's a really. Oh, I see what this is a dot, and then a plus sign. Oh, that looked like a 7. I was like, that looks kind of weird. So that's an n squared over 2 to the n, and then it's an n plus 1 squared over 2 to the 1. So the idea here is that basically this term divided by that term is essentially 1/2. And if we look at the actual n plus 1 term over the nth term, we get n plus 1 squared over 2 to the n plus 1 over n squared over 2 to the n. Flip and multiply, you get this 2 to the n over 2 to the n plus 1, and then you get this n squared over n plus 1 squared. The 2 to the n over 2 to the n plus 1 just becomes a 1/2. And the n plus 1 squared over n squared becomes n plus 1 over n squared. But n plus 1 over n, if you take the limit, goes to 1, and then 1 squared is just equal to 1. So you get 1/2 times 1, which is 1/2. So basically what we're saying is the quote unquote ratio of this quote unquote geometric like thing is 1/2. And so if the limit of this ratio is equal to a number that's smaller than 1, it's essentially like saying our ratio is smaller than 1, and we're going to get a convergent geometric like series. So the idea of the ratio test is exactly what I wrote before. If you take the limit of the next term over the previous term, usually there's an absolute value there. If that's equal to some number that's less than 1, you get convergence. If that ratio is equal to some number that's bigger than 1, you get divergence. And that limit's equal to actual 1, you get no results. So for example, you could totally find whether or not this convert. We should leave off the factorials for now. We'll talk about factorials later. But just for example, you could totally say, does this series from, let me look at a quick example. Sorry, so I'm going to give you one example before I end this. Sure. And most of them do involve factorials, unfortunately. I know. So I want to find like the sum from n equals 1 to infinity of n cubed over 4 to the n. Well, again, I'm going to take the limit as n goes to infinity of my a sub n plus 1 over a sub n, which is really going to be the limit as n goes to infinity of n plus 1 cubed over 4 to the n plus 1 over n cubed over 4 to the n. Now, quick tip here. Whenever you do something like this, people almost always skip this step and jump straight to writing it as the n plus 1 term multiplied by the reciprocal of the nth term. So instead of dividing by n cubed over 4 to the n, multiplying by 4 to the n over n cubed. Then we group like terms. So remember, this is the limit as n goes to infinity of n plus 1 cubed over n cubed times 4 to the n over 4 to the n plus 1. Then we simplify. Make the limit as n goes to infinity of that's an n cubed there, sorry. N plus 1 cubed over n cubed is n plus 1 over n cubed. And 4 to the n over 4 to the n plus 1, you can cancel 4 to the n, you're left with just a 1/4. And then what usually happens with this, you can rewrite it if you want to, but yeah, and I like rewriting it. N plus 1 over n is just 1 plus 1 over n to the third times 1/4. And then as n goes to infinity, 1 over n goes to 0. You get 1 to the third. So you get 1 times 1/4, which is 1/4, which is less than 1. So since this limit of this ratio is less than 1, we can then say our series converges by the ratio test. Okay, that's all I got for today. See you all on Monday.